Let's look at an interesting problem. So we have a beaker full of water with holes at different depths, and from those holes, water is being ejected out and it is hitting the ground at different distances. So the question asks, is something wrong with this diagram? So here we have a completely normal beaker filled with water with holes at different heights. Nothing seems to be wrong with that. What about this part? Can there something be wrong here? Possible. Let's try to find out. So from this diagram, what they seem to be claiming is the deeper the hole is from the water surface, let's call this depth h, the further the water jet will reach before hitting the ground. Is this really true? Intuitively, it seems that way because the velocity with which the water is being ejected out, which is also called the velocity of efflux, that increases the deeper you go from the water surface. So, like we know that velocity of efflux is root of 2gh. So, it is proportional to the root of the depth below the water surface. So, as the depth increases, the velocity will increase, and intuitively, the faster you throw something, further it will go. But if you look closer, there is actually one more conflicting parameter that is deciding this range. What is that? The deeper I go, true, the velocity of efflux will be higher, but at the same time, it will have lesser time to travel through the air before it hits the ground. Just to make this point obviously clear, if we throw something with this very same speeds from different heights, obviously the one which is higher will cover a higher horizontal range than the one thrown from a lesser height. Here I am talking about the height above the ground. So if this scenario is not true, what is the actual scenario? What is this range and how it is dependent on this depth? If we throw an object horizontally like this, the range it covers is given by where the d is the height from which this object is being thrown and v is the velocity with which it is being thrown. So I'm not going into the details of how we come to this or this because these are pretty standard stuff and it's not the point of this discussion. So if it is not clear, you can go and take a look. From this scenario, what is this v? This v is nothing but root 2gh. And what about this d? This height of this hole? It is actually the total height of the water column minus this depth. I'll just replace the d so that we can compare based on this one variable, which is depth below the surface. Bit of simplifying, we can see this is actually 2. So this is what the horizontal range looks like. Now we can analyze what is the actual profile of this horizontal range for various depths h. So you can see this part here, this h into h minus h, this is actually a quadratic function in h. So it looks something like this, minus of h square plus h into h. This square root is a monotonically increasing function. This is how this range will vary with respect to h. So what does this quadratic look like? As we can see, as the depth below the water surface increases, indeed, the range also increases, but it increases to one point, after which if we increase the depth, the range starts to decrease. So what is this depth till which the range will keep on increasing? For a quadratic of this form, we know that the maximum occurs at point x equal to minus b by 2a. So using this comparison, minus h by 2 into minus 1. So it's basically h by 2. So half the depth will get the maximum range. So this is what the scenario actually looks like. At a depth of h by 2, the jet reaches its maximum range. And from either side of this point, the range gradually goes on decreasing as we move further away from this center point. So yeah, the situation described in that diagram was indeed not true.